So good morning, everybody, and thank you very much, Monique, for the introduction. So indeed, the title of my talk is as shown, and it's joint work with Daniel Brosch, who is a PhD student of mine, but he's not the ESR for Poema. He's in fact ESR for a sister project on a mixed integer nonlinear optimization called Minoa. So this is actually the second time this has happened because Lukas Slot gave an earlier presentation in this meeting, and he's also ESR from that project. So this might seem a bit strange, but there is a reason why I wanted to talk about this topic, and that is because we had these nice Poema days, and one of the series of talks was by Cordian Riener, who spoke about symmetry reduction for polynomial optimization problems, but also more general for conic optimization problems. And he focused on how to exploit the group representation theory. So this topic of today is a bit complementary to that, because it's also about reducing the size of conic optimization problems through pre-processing. But this time the groups are not visible. So this is a technique that you can even use if you have absolutely no idea about the symmetries in your problem. So I will discuss the theory and some extension to doubly non-negative matrices. So these being the positive semi-definite matrices that are also entry-wise non-negative. And then I will also discuss some software that Daniel has written that you can try yourself to exploit structure in conic optimization problems. Okay, so without further ado, what I would like to discuss is conic optimization in general, and over the doubly non-negative cone in particular. So just to remind you again, these are the positive semi-definite matrices that are also entry-wise non-negative, hence the name doubly non-negative. Okay, and then these problems appear in many places, and most frequently in conic programming relaxations of combinatorial problems. So we're going to look at an example, which is the relaxation of the quadratic assignment problem. So this is just an example of a combinatorial optimization problem that is notoriously hard to solve. And semi-definite programming relaxations have been quite successful in making progress on solving such problems. So it is of interest to try and solve these semi-definite programming relaxations, and in particular, to exploit any asymmetries that are present in the problem. Okay, so the specific type of reduction that I want to discuss is not something that was covered by Cordian in his survey talks. So this is called Jordan symmetry reduction. It's a very recent development from people at MIT. And this is by Pablo Parello and his former PhD student, Frank Permenter. And this work has just basically appeared this year in a journal. But much of it was contained in the PhD thesis of Frank Permenter. I will give the reference to the PhD thesis right at the end. So what is the idea? So basically the idea is, like I said, this is in some sense the most general framework for reducing conic optimization problems. And it works even if you have no idea about the symmetries. So the downside is that you must be able to do basic linear algebra operations with the data that you have. So that is of course a disadvantage. But as long as you can do basic linear algebra operations, you can implement it, and you need not understand the structure of your problem. So this makes it also very suitable for pre-processing software. Okay, and then what I would like to do is also this theory by Parello and Permenter. Basically, this only works for certain cones, in particular symmetric cones. So for our purposes, if we work in the spaces of matrices, these are just positive semi-definite matrices or Hermitian positive semi-definite matrices. So what we would like to do is to study these doubly non-negative cone problems, because they arise, like we said, in examples. And I would like to share with you what we could find out about the extension of a technique to these cones, which are non-symmetric. And yeah, so I do not want to exaggerate our results, but because we, you know, this is a very difficult problem, but we do have some insights which I would like to share. Okay, and in particular, Daniel Broche, my PhD student, actually implemented some Julia software. I would just like to share this with you because perhaps this is useful to you. And then I would just like to show some nice numerical examples of relaxations of quadratic assignment problems that we could solve with this algorithmic framework that Daniel implemented. Okay, so that's the plan for today. So we start with conic optimization, and in particular, looking at the doubly non-negative cone. So here is the general conic optimization problem, and I think many people here are very well familiar with these things. So basically, it's a linear optimization problem, and the only nonlinear part is the membership of the cone. So K is in principle a closed convex cone in an inner product space. Yes, so we have an objective function defined by the inner product and a data matrix C. We have some linear constraints defined by elements AI and right-hand side values BI, scalar values. And then we have the cone membership. Okay, so of course, this is abstract, but we're going to be interested in the case where this is either the cone of parts of semi-definite matrices or the doubly non-negative cone. And moreover, it's going to be to understand the Jordan reduction framework, it will be more convenient to rewrite this problem by just making by just saying that, okay, these constraints imply that X belongs to some affine subspace. We're just going to make this explicit by saying X belongs to this affine subspace, where X0 is just any point in the affine subspace defined by these conditions, and L is a suitable linear subspace. And of course, L should be the null space of the linear operator defined by the left-hand side here. So L, we can just choose as a null space of this linear operator, which maps things from the space that we work in to Rm because of these conditions. Okay, so this is very well known, quite standard. Maybe just the notation is slightly unusual, but this is usually called the standard form for conic optimization problems. And this is the alternative form that is a bit more suitable for our purposes. Okay, so having said that, just again, we are interested especially in the case where this ambient inner product space is just the space of symmetric matrices. So Sn denotes for me the n by n symmetric matrices, and we just equip it with the Euclidean inner product, or it's also called the trace inner product. And then in particular, we're interested in the case where K is the cone of doubly non-negative matrices, and we just give it a name. So the n by n doubly non-negative matrices we will denote by Dn. And and sometimes we will also be interested in the case where K is the positive semi-definite cone of order n. Okay, so I think very clear so far. So, so why are we interested in such problems? Well, these problems arise as convex relaxations of different problems. So one example is, which is relevant to Poema, is if we have polynomial optimization problems with non-negative variables, then we can use semi-different programming relaxations. And sometimes hierarchies of semi-different programming relaxations like the Lasserre hierarchy. But because we are working with, we are relaxing problems with non-negative variables, these doubly non-negative matrices then appear quite naturally in these semi-different programming relaxations. And of course, combinatorial optimization problems, you can view them as polynomial optimization problems with non-negative variables, typically 0, 1 variables. So indeed, then, in a special case of combinatorial optimization problems like the quadratic assignment problem, we arrive at doubly non-negative matrices through convex relaxations. So I just want to have one running example with which I can illustrate the theory and the computation. So this example is going to be the quadratic assignment problem. And I'm sure not everybody is equally familiar with this. So let's just look at this together. So this is called the quadratic assignment problem. it's a problem defined by two matrices, a matrix A and a matrix B. Let's just say they are symmetric matrices. And what we want to do is we want to kind of sum the entries of A times the entries of B after allowing ourselves to permute the rows and columns of the matrix B. Okay, so formally we are minimizing over all permutations of n elements, the rows and columns, let's say, of the matrix B. So we can just write this as this is just a permutation element of the symmetry group on of order n. And then we are trying to minimize this expression. Okay, so indeed, so this looks like the inner product of a matrix A with a Euclidean inner product of the matrix A with a matrix B, but we allow ourselves to first permute the rows and columns of the matrix B through a permutation phi, and then we take the minimum value over all possible permutations phi. Okay, so this problem is actually remarkably useful. So it was studied first by the Nobel Prize winner Koopmans, I think, yes, in the context of facility location problems. But it has several other applications. We will see later in this talk application from physics, and it also models other combinatorial optimization problems. So it generalizes, for example, the traveling salesman problem. And so it is an NP-hard problem, but more than that, it's also notoriously difficult problem to solve. So in practice, if you want to solve these problems for matrices of size 30 by 30 to global optimality, then this is a real challenge. So, I mean, it's not like the traveling salesman problem that you can often solve to optimality even for thousands of cities. These are really difficult problems, not just theoretically, but also in practice. Okay, so what does the typical convex relaxation of such a problem look like? Well, before I do that, I would just maybe like to rewrite the quadratic assignment problem a little bit on paper. So I just share my camera with you. Okay, so yeah, so now this is the quadratic assignment problem that we just had on the slide, but we can always also rewrite it in terms of permutation matrices. So we can also rewrite it, of course, we can associate the elements of a symmetric group with permutation matrices. So I can say we take the minimum over the set of permutation matrices of order n, which I just denote by pi n. So pi n are the permutation matrices of size n by n, and then we can rewrite this as the trace of the matrix A times x b x transposed. So it's a simple exercise to see that this is exactly the same. So we just make sure that the permutation matrix X corresponds to the permutation phi. And then just using properties of the Kronecker product, we can just rewrite this again as follows. So we can take the trace of bigger matrices. So we can do B Kronecker A, and then we have a matrix here where we vectorize X and times the transpose of the same vector. Okay, so by vectorize, I just mean we concatenate the columns of X. So we just stack the columns of the matrix X to form a vector of length n squared. And then the last thing is we can give this thing here a name. So we can call this a matrix Y, which is going to be a positive semi-definite matrix by construction. And it's also going to be greater equals 0. So we get that Y is definitely an element of the doubly non-negative cone of order n squared. So you see this, and this gives us the basis for convex relaxations that are used in practice. So let's just going back to the slides. Yes. Okay, so going back to the slides, then we can see a semi-definite programming relaxation. In fact, relaxation over doubly non-negative cone. from the literature. And I mean, it looks very scary on the first instance, but if you just look at the objective function, this minimizing the inner product, which is just a trace of B Kronecker A times Y, this is precisely how we had rewritten it. And then we said that Y had to be this dyadic product of vec X times vec X transposed. But I mean, that we just said that it implies the fact that Y is in the doubly non-negative cone. So I mean, we understand this part and then that part. And then these linear conditions, you can just verify for yourself if Y is indeed this dyadic product of the vectorized permutation matrices, then all these constraints will hold. So just the notation, I is the identity, J is the all ones matrix, and these EJJs, they are just 0, 1 matrices with only one non-zero element on the diagonal at the position JJ, or if you will, it's just this dyadic product for the standard unit vector. Okay, so it's just a nice exercise for students to verify that this is indeed a relaxation of the quadratic assignment problem. If one substitutes the Y as vec X transpose, then indeed you get a feasible solution for this. So, but we're dropping the rank 1 condition on Y, so we get a lower bound on the optimal value of the quadratic assignment problem. So this particular relaxation was introduced in '98 by Zhao, Karish, Rendel, and Volkowitz, and this specific reformulation is due to Powell and Rendel a bit later. Okay, so in practice, we like to solve problems like these. They tend to give really good lower bounds on the solutions of instances of the quadratic assignment problem. And quite often there is some hidden structure in these problems. So the structure, of course, comes from the matrix B and the matrix A. So I mean, these matrices might have large automorphism groups, or they might have some other algebraic structure, and we might not know beforehand what the structure exactly is. Okay, so then this brings us to how to exploit the structure through symmetry reduction, and in particular this new type of Jordan symmetry reduction. So recall our conic optimization problem. So this was just the rewritten form. We minimize the C inner product X, and X belongs to this affine space and to the cone K. And for all types of symmetry reduction, the idea is just to restrict the optimization, or the ambient space, if you will, to a low dimensional subspace, let's say S of the ambient subspace, that is guaranteed to contain an optimal solution if there exists an optimal solution. Okay, so the whole point is, if we can restrict to a low dimensional subspace without loss of generality, then we need fewer variables to express the unknown. Now, if we can express it in terms of the basis of the subspace, so that cuts down the number of variables in the computation immediately. But there is also usually an extra advantage to doing this, because in particular, we are interested in restricting to subspaces that have additional algebraic structure. So typically, this subspace that we restrict to also is an algebra. So maybe a matrix star algebra for our cases, or some other type of algebra. And that can be further decomposed. So Cordian spoke at length about these decompositions, but for practical purposes, the interesting thing is that we can typically simultaneously block diagonalize the basis matrices of the subspace, and that we can then exploit when solving these problems, because it's nicer to deal with membership of the cone of some small matrices than a big matrix. Okay, so then now I want to discuss a little bit more details about the approach of Parellio and Permenter. So we're going to find such a suitable subspace S, and the discussion is going to be framed in terms of the orthogonal projection onto S. And so P of S, P always stands for P of S always stands for the orthogonal projection onto the set S. Okay, so again, just the notation of the orthogonal projection. And now here is the key object. We call S an admissible subspace for a conic optimization problem that we're studying under some conditions. So again, this admissible subspace is just going to be a subspace where we can restrict the optimization to. And basically, so if we restrict the variable x to belong to this S, we will not lose anything. It will be without loss of generality from the optimization perspective. And the conditions are as follows. First of all, the orthogonal projection onto S must map the cone K into itself. So this is sometimes called cone positivity condition of the projection. The second thing is it must also map the affine subspace x0 plus L into itself. So if we just look again at the conditions for feasibility, x belonging to the subspace and x belonging to the cone, then you see that these first two conditions guarantee that we map feasible solutions to this problem to our feasible solutions. Okay, and what's a little bit less obvious is that this last condition guarantees that the objective function does not change if we do this projection. Okay, so the point is just, you know, if we have a subspace S and we have these properties of the orthogonal projection onto S, then we are guaranteed that we can restrict the optimization to S. So here is it in words. So formally, if the conic optimization problem has an optimal solution, then there is an optimal solution in S. So this just means that we can just restrict X to the hopefully low dimensional subspace S, and then that can cut down on computation. Okay, so the nice thing is that one can simplify these conditions, which are a bit hard to deal with in the case of special cones, and in particular for the cone of positive semi-definite matrices, so Sn plus. So basically, one of the conditions of for admissible subspace was that it should be cone positive. It should map the cone into itself. And for the positive semi-definite cone, this condition of cone positivity is equivalent to the subspace S being closed under taking squares. So these are just squares by normal matrix multiplication. Okay, so that's quite interesting. So the cone positivity for the positive semi-definite cone then is the same as the subspace S being closed under taking squares. And yeah, so I presented the theorem in this way, but it's actually true in a bit more general setting. So basically, we're now here, and for this theorem statement, we are working with the ambient space being a symmetric matrices, but it also works if we are working in any special Euclidean Jordan algebra and K being its cone of squares. So I don't want to frame it in the most general terms, because then I would have to explain what the Euclidean Jordan algebra is, which I don't want to do, and especially not what the special one is. But so for our purposes, we work with matrices. So just take it from me that the symmetric matrices is a special Euclidean Jordan algebra, and its cone of squares is the positive semi-definite cone. So just to say at least a couple of words. So if we view the symmetric matrix as a Euclidean Jordan algebra, then of course we must have a multiplication, and it must be closed. So Sn must be closed under this multiplication. So then if we define the product of two symmetric matrices as this, so obviously this results in a symmetric matrix. And so basically then the condition that S is closed under taking squares means that S is a Jordan subalgebra of the symmetric matrices. So why is this the case? Well, it's just the simple identity that holds more generally for Euclidean Jordan algebra. So the product we can write in terms of squares. So you can just verify, it's just very easy to verify indeed that the Jordan product of the two symmetric matrices we can just write in terms of squares, where these squares refer now to the normal matrix product. And which is of course the same as the square for the Jordan product. But the point is this: so if a subspace is closed under taking squares, then all these things belong to the subspace, and of course it's a linear subspace. It's a linear subspace, so the whole thing belongs. So it's closed under taking the Jordan product as long as it's closed on the taking square. So that's if and only if. So this second condition actually means that S must be a Jordan subalgebra of the symmetric matrices. So this is really nice. This compositivity condition is well understood in the case of the positive semi-definite cone. So so the problem is just that if we look at general admissible subspaces, there is no real computational procedure to try and find them. It's too complex. But if we restrict to special subspaces, then it becomes more tractable. So a specific type of subspace that we have in mind for the purposes of computation is called a partition subspace. And this is a very simple thing. It's just a subspace of Sn that has a 0-1 basis that sums to the all ones matrix. Okay, so if we would look at symmetry reduction through group theory, then these partition subspaces usually arise as orbitals or orbits of pairs. But I mean, if we do not consider the groups, then we can just consider the abstract notion of a partition subspace. And then just to give you a simple example, so here P1 and P2 are two partition subspaces, or denote two partition subspaces for the case n is equal to 3. So you can see P1 denotes a three-dimensional partition subspace. So we have three basis elements. One has ones here and zeros elsewhere. One has a 1 here, zeros elsewhere, and one has ones where the b's are and zeros elsewhere. Similarly, P2 is another partition subspace, also of dimension 3. And then we have, for algorithmic purposes, we have this notion of refining both partitions. So we have this operation, this is AND operation. So we say partition 1 and partition 2 is in fact the lowest dimensional partition subspace that contains these two partition subspaces as subspaces. So for example, you can see this one has the same element here, but these two are different. So in the AND operation, we need them to be different. But in all cases, these elements are the same. So this can also be the same in the refinement. And this is a unique element. So that's also fine for the refinement. So this denotes the lowest dimensional partition subspace that contains these two subspaces as subspaces. Sorry, too much overuse of the word subspace. Okay, but I hope you get the idea. And then there is a simple algorithm given in the thesis of Permenter that allows us to compute the optimal admissible partition subspace. So this is very important. So we do not know how to compute the optimal admissible subspace even for the positive semi-definite cone in general. But if we restrict to partition subspaces, then this algorithm does the job. Okay, so just we do not have to look at the details too much, but just to explain. So just we just need an operation for operator part that returns the partition corresponding to the unique entries of the matrix. So part of a matrix just looks at the unique entries of a matrix, and based on that associates with it a partition subspace. Okay, I think this is very clear. So then the first thing that what one can show in this case is the admissible subspace must contain the orthogonal projection onto L of the matrix C, which is of course one of the data matrices, and the orthogonal projection onto the orthogonal complement of L of the point x0, which was also part of the data for us. Okay, so basically we just start with the partitions of these two elements that have to lie in the admissible subspace, and we do this refining of the partition. And then basically, so basically then we do some simple operations. So the second operation we can actually do in a randomized way. We can just take a random element x from our current partition P and square it, and then refine our partition with respect to the partition of the square. So I mean, it might not be obvious to you that this is implementable, but it actually is. And I mean, the only operations that we are actually performing is doing this refinement of partitions. and the squaring. So essentially, you know, we look at the matrix, we look at some partition, and then we look at the symbolic element, we square it, and then we look at the partition of this element, and then this gives us a new partition, and then we do a refinement with respect to this partition. So for those of you who know these things, this is very, very similar to an old algorithm by Weisfeiler and Lehmann that was used to study the graph isomorphism problem. But this is just slightly different because we are working with symmetric partitions. It's not clear that I will explain in a second why it's not clear that it's exactly the same as the Weisfeiler-Lehmann algorithm. But if you know that one, then this might be familiar to you. Okay, so let's just recap. So we have partition subspaces of the symmetric matrices, and sometimes, you know, these things are also closed under taking squares. So they're also Jordan subalgebras. And if this is the case, that such a partition subspace is called a Jordan configuration. Okay, so basically a partition subspace, which is also a Jordan subalgebra, Euclidean Jordan subalgebra, then it's called a Jordan configuration. So those of you who know something about algebraic geometry, you will, algebraic combinatorics, might know coherent configurations. So coherent configurations are also 0-1 bases of matrices, but then we don't have the symmetry requirement, but we do have a requirement that they form a basis for a normal matrix star algebra. So it's a kind of a generalization of the idea of Jordan configurations to a non-symmetric setting. And then it follows that the symmetric part of the coherent configuration must be a Jordan configuration. So indeed, these objects are well studied. And basically what the Weisfeiler-Lehmann algorithm does is if you have a non-symmetric type of partition, then it will find for you the smallest dimensional coherent configuration that contains it. Okay, and so basically, if we focus on symmetric parts of coherent configurations, then we are in fact dealing with Jordan configurations, but it's not clear if the converse is true. So this is an open problem. So in some sense, you know, this is a bit frustrating. It's not 100% clear if this Jordan reduction approach actually extends the known approaches like with Weisfeiler-Lehmann that computes coherent configurations. It could be more general, or it might still turn out to be the same. Okay, so just this algorithm that we had on the previous slide to find the optimal partition subspace, it actually outputs a Jordan configuration because, you know, by its construction, it's closed under taking squares. So because what we are doing is we keep finding these partitions, and we keep ensuring that they are closed under taking squares because we keep squaring them. So indeed, and this is as it should be, because we already said that any admissible subspace must be a Jordan subalgebra when we are dealing with the positive semi-definite cone. Okay, so we are getting some feeling for at least for the positive semi-definite cone, and when we can compute the admissible subspace, in particular, we can compute the optimal admissible partition subspace. Okay, so now I just want to say to you, you know, where do we get stuck, or how far can we get extending the results from the positive semi-definite cone to the doubly non-negative cone, because it's a different ball game. This is not a symmetric cone. So the first thing, which I call a theorem, but it's actually a simple observation, but it's the basis of the computational approach. So this is by Daniel and me in one of the papers I will show later. It's just, if we consider optimization problem with a positive semi-definite cone, and we have an admissible partition subspace for this thing. Okay, so admissible partition subspace, so we can compute this thing. Okay, then this admissible partition subspace we've computed for the positive semi-definite cone is also an admissible partition subspace for the problem where we replace the positive semi-definite cone by the doubly non-negative cone. Okay, so in some sense, any admissible partition subspace for the problem with the semi-definite cone here is also an admissible partition subspace for the problem with the doubly non-negative cone here. And then, of course, the practical implication is what we may use this algorithm I showed you to find an admissible partitionable subspace for the doubly non-negative cone. So we just do it for the semi-definite cone, and what we get out of the computation is also a admissible partition subspace for the doubly non-negative cone. Maybe not minimal, but it is admissible partition subspace. Okay, so that's one thing. So basically, the next thing that we have to understand, if you want to have a deeper understanding, is that every admissible subspace is cone positive. So indeed, if we consider the doubly non-negative cone, an admissible subspace S must be such that the orthogonal projection of the doubly non-negative cone must be contained in itself. And so basically now I ask the question, how restrictive is it really to only look at partition subspaces? So the answer is it seems to be not too restrictive if we deal with a doubly non-negative cone. So let me just give you a less trivial result that we showed. So basically we say that if a subspace contains the identity and the all ones matrix and it's cone positive for the doubly non-negative cone, then it has to be a partition subspace. So you see, what this says is any admissible subspace for the doubly non-negative cone that contains the identity and the all ones matrix already has to be a partition subspace. So in some sense, the restriction to partition subspaces is not that strong. So then if also we know that this projection onto S is cone positive for the positive semi-definite cone, then S also has this algebraic structure that it's closed under taking squares. So it is in fact a Jordan configuration. So but unfortunately, this extra assumption is not something we like. So this is an open question for us. When does cone positivity, for which subspaces does cone positivity for the doubly non-negative cone actually imply cone positivity for the positive semi-definite cone? So I always enjoy the story of Georges Polya, who had John von Neumann in his class at some point, and he said that Polya liked to post open problems during his lectures, and he said that on more than one occasion von Neumann just brought him the answer at the end of the lecture. So don't be shy. I would be very happy if someone knows the answer to this. Okay, so just to move on to an example. So now I just want to show you how this computational framework works for one specific application of quadratic assignment. And this is an application in physics called energy minimization on a toric grid. So in particular, the problem is as follows. We have a toric grid shown like this. So the grid points, in my perspective, are actually the squares. So I want to place particles on the grid points, which just means I'm coloring some of these squares black. And there is a certain grid size to this. So this is, in this example, it's an 8x8 grid. So you can count 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Sorry. The joys of working from home. Okay, so and the point is that this toric grid we can also interpret as a tiling of the plane. So here we have an 8x8 toric grid, so we can also view it as a repeated 8x8 grid here, which we can use to tile the entire plane. And so the idea is to put these particles on the grid in such a way that they correspond to a minimum energy configuration. So what does this mean? So these are repulsive particles. So in some sense, they will be as far apart as possible. And exactly what is the meaning? So we associate a certain energy between two particles, which we want to minimize, and the energy is inverse to the distance between the particles. So the distance in this case is the lead distance, just the shortest path on the grid. So in this case, it's 1, 2, 3, 4, 5. Or if you want 1, 2, 3, 4, 5 is the distance between these two particles on the grid. So basically, we want to place a certain number of repulsive particles, we call it M, on an n by n tori grid in general to minimize the total energy of the system. So this is the example. And this is indeed a quadratic assignment problem. So not to give too much detail, so basically we just have to define the two matrices of the quadratic assignment problem. So the one matrix A is just a 0, 1 matrix with a block of ones in the upper left corner. And the matrix B will encode this energy between particles when placed at certain grid points. So the matrices A and B are indexed by the grid points. So their order is a number of grid points. So in the example, we had 8 by 8, so 64 grid points. So in that example, these will be 64 by 64 matrices. So the matrix A is just some simple 0, 1 matrix. And B Bij is given at the inverse lead distance between the grid points I and J. So it's well defined. And then if we minimize this thing, we are in fact minimizing the total energy of the system. Okay. So so it's also just it's just a matter of puzzling a little bit. Then you'll agree with me. This is in fact, this expression gives the energy of the system if the phi in some sense corresponds to the placement of the particles. Okay, so this example is actually of some relevance. So it has some application in physics as to grayscale printing, and some things are known. So in particular, if we have a square grid and we want to put particles M on half the grid points, then so-called chessboard configurations are known to be optimal. And the fact that chessboard configurations are optimal is known from this paper by Baumann et al. And they showed it using some lower bound, which was not computed by semi-different programming, but it was a simple eigenvalue bound and called PB. Okay, and just to show you some numbers, so here are some examples. So for example, here is a 10 by 10 grid, placing 20 particles. And then this is the bound we computed with Jordan reduction. This is an upper bound you can find from a heuristic, and this was the eigenvalue bound. So this showed that what we could do with symmetry reduction, with Jordan reduction, we proved that a certain configuration is optimal. And then we can just make some pictures of optimal configurations. For example, it will not surprise you that this one is optimal, and the chessboard one was known to be optimal. But for example, this is also optimal for 12 particles, and not so much new in 7 by 7. But we can continue, and for 10 by 10, for example, again, the chessboard was known to be optimal. But for example, this one that is generated by some types of knight moves, this is also optimal for 20 particles on a 10 by 10 grid. And we could actually do some extensive computation for up to 100 by 100 grids, establishing optimal configurations in this way. Okay, so just to conclude, my student Daniel Broche actually implemented a nice Julia package called STP symmetry reduction, which is available on GitHub. And it includes routines to find this admissible Jordan configuration using a randomized version of the algorithm I showed you. It also can block diagonalize the basis. And then it has some specialized routines for this QAP relaxation to formulate it, reduce it, and solve it using Jump and Mosaic, the STP solver. And it also has a specialized routine to compute the Lovász-Schreiber theta prime function of a graph. And this can be done for large graphs if they have a lot of symmetry. For example, if the automorphism group of the graph is very large. Okay, so perhaps you can try this, and maybe this is of some interest to you. And I conclude just by saying. My talk for today was based on two preprints with Daniel Broche. So basically this part about the Jordan reduction for doubly non-negative cone, what we can say about it, and the Julia software that Dandel implemented, this is described in this archive preprint. And this work for the energy minimization problem was actually earlier work described in this preprint, and this has actually already appeared in discrete optimization. So if you're interested, you can read more. And then also just I could only say a very few things about this theory of Jordan reduction, but I hope you get the impression that this is a very significant theory and very interesting, and it's really beautifully presented in the PhD thesis of Frank Permenter. So this is also online. So if you're interested, you can read more. So I thank everybody very much for your attention.